All right, so chapter 13, where we explore equilibria. That is the plural of equilibrium. So, what is an equilibrium? Now, we write chemical reactions, for the most part, as if they only go in one direction, from reactants to products. Hate to break it to you, but that's not the way things are. Okay, there's nothing that tells a reactant that it's a reactant and not a product, and vice versa. You can just as easily go in the reverse direction. And, in fact, pretty much every reaction does, to one degree or another. So, here's what happens when you look at a real reaction, an equilibrium reaction, I should say. Okay? You start off with just reactants. Okay? And they start reacting. And initially, the forward rate of reaction is high because you have a lot of reactants. Now, over time, the products start to build up, and the reverse, the reverse arrow didn't show up here, but that square is a reverse arrow. The reverse reaction starts to build. The products start to build up. The reverse rate increases as the forward rate decreases. Okay, and what that was actually, that wasn't a reverse arrow, sorry. It was a double arrow, only the forward arrow was bigger than the small arrow. Okay. Eventually, what happens is you reach a dynamic equilibrium, where the forward reaction is equal to the reverse reaction. Okay, or I should say the forward rate is equal to the reverse rate. It's called a dynamic equilibrium because it's in constant motion while staying still. If you've read Alice in Wonderland, that's like the Red Queen, where you run as fast as you can just to stay in one spot. Okay, you think of it as the population of a city, where people are constantly going in and out of the city, but the population of the city remains constant. So that's what happens with a dynamic equilibrium. A static equilibrium, by contrast, it's staying in one spot and nothing's happening. You know, a chair sitting on the floor, it's a static equilibrium, no motion. Dynamic because there's constant motion. Now, technically, all reactions reach equilibrium. It's just that some reactions lie so far to the right, over in the product side, that you can pretend that it's not in equilibrium. Okay, so hydrogen and oxygen making water, the combustion of octane, these all lie so far over in the products that they're just not going to go in the reverse direction. In the case of water, it's because it's incredibly energetically unfavored. Okay? It wants to be, that should be 2H2O, damn it. It's unbalanced. Okay, but it really, really wants to be water rather than hydrogen and oxygen. Okay? In the case of octane being combusted, not only is it very energetically favorable to be carbon dioxide and water instead of octane and oxygen, but just look at those numbers. It's very, very unlikely for carbon dioxide and water to combine in such a way as to make octane. Okay? It would take a lot of coincidences, energetically disfavored coincidences. Like things just randomly falling uphill over and over and over again. So it just doesn't happen. All right, moving on. How do we characterize equilibria? How do we describe them? That's what we have the equilibrium constant for. Okay, it's a ratio of products to reactants. Okay? So for this reaction, A plus B going to C plus D in equilibrium, okay, the equilibrium constant, that's KEQ, capital K, sub EQ, is equal to the concentration of C raised to the C times the concentration of D raised to the D, divided by the concentration of A to the A and the concentration of B to the B. Okay? And in this case, the exponents are the coefficients. Okay? The equilibrium constant is nice and easy to remember. Products divided by reactants. Now, similar to the rate constant, this is for a particular temperature, but it works quite well. If you let a system reach equilibrium from any starting point, any mixture of reactants and products, it will always reach an equilibrium state such that products over reactants is equal to that equilibrium constant. Okay? So you can start all the way over on the product side, you can start all the way over on the reactant side, you can start off with equal mixtures of reactants and products, you can start off with equal amounts of reactants and no products, you can start off with wildly different numbers all over the place. No matter what, it would eventually reach an amount of reactant and product such that products over reactants equals the equilibrium constant. Okay? All right, now let's continue on the next slide. That's enough about that. We will be doing lots of math, I'm sorry to say, but let's move on to pressure. Because the equilibrium constant doesn't have to be done just with concentration. You can also do it with pressure. And now I see I made a mistake on this slide. Because the equilibrium constant for pressure, you see it's sub P instead of just sub EQ, it's products over reactants still, but they should also be raised to the powers of the coefficients. Okay? It looks exactly the same. It's just that you've, instead of measuring concentration, you're measuring pressure. The numbers aren't the same. Okay, obviously, concentration and pressure aren't the same thing. So the equilibria for pressure and concentration likewise are not the same thing. And there is a way to convert from one to the other. It's not hugely important, but it's out there if it's if it ever becomes an issue. But you can also do equilibrium problems with gases, is what I'm saying. It doesn't have to be dissolved solutions. It can also be mixtures of gases. The reason we focus on these two mostly is because gas phase chemistry and solution phase chemistry are both really easy to work with. They're easy to handle in small quantities or in large quantities, so you can do it in a research laboratory or you can do it in an industrial setting. And let's face it, you look inside of the human body, that's pretty much a big old mess of a micro-scale factory of solution chemistry all over the place. So, I mean, most stuff we deal with is going to be either gas phase or in solution. But KEQ and KP, either one, we're talking about homogeneous stuff there, or at least that's what we've implied. You also get heterogeneous chemistry. That is to say, when you have different phases showing up in the same reaction. And when that happens, solids and liquids don't show up in the equilibrium expression. Okay, they're just completely absent. Okay, or I should say that undissolved solids and pure liquids don't show up in the equilibrium expression. The equilibrium expression, excuse me, not the reaction. They do show up in the reaction. They don't show up in the equilibrium expression. Okay? So that's one of the reasons why it's important to have the phases written on the substances involved in the reaction. Okay? So for example, here we have water and carbon dioxide combining to form carbonic acid. And we see liquid water and aqueous CO2, so dissolved carbon dioxide, react to form aqueous or dissolved carbonic acid. And the equilibrium expression for that is just the concentration of carbonic acid divided by the concentration of CO2. Water doesn't show up. It doesn't play a part. There are various reasons for that. Among them, that the liquids involved in these things typically are involved in such high concentrations. If you're writing it as a liquid, then it's usually the solvent rather than a solute. Okay, so for example, you dissolving carbon dioxide in water. There's so much more water than carbon dioxide that it's not helpful to include the water. It would just sort of swamp any equation or any math you tried to do with it. So you leave it out. Okay, it is for all practical purposes not going to change. You don't include solids because what you're measuring here is sort of related to kinetics, sort of related to energetics. And changing the amount of solid, you're not really going to change the way it's interacting with the other things. whereas changing the concentration of something will change how likely it is to run into other things a whole lot. You know, a solid's just going to sit there in terms of kinetics. You don't include liquids and solids in the equilibrium expression. But gases will show up as pressures, and dissolved things will show up as concentrations. But what can we do with equilibrium constant? Well, before we get into the math of working with the equilibrium constant, let's look at Q. Q is the reaction quotient. You calculate it the exact same way as you would the equilibrium constant. The difference is that Q is anytime, K is only at equilibrium. So then you can compare Q to K. Okay. So you have K, it's been measured, you know what it is, and then you have some system. You measure Q and then you compare it to K, and that'll tell you where the system is in comparison to where it wants to be. It wants to be at equilibrium. Okay, so if you measure Q and it's smaller than K, that's telling you that P is smaller than it wants to be, R is bigger than it wants to be. Okay, so you have too much reactants. Okay, so it's going to move toward the products. Whereas if Q is bigger than K, you have too much products, not enough reactants. It's going to move toward the reactants. And if Q equals K, of course, that means that you are at equilibrium. And now I want to talk about some of the vocab. Okay. When Q is greater than K, okay, you have too much products, you're too far into the products, you're too far over toward the product side. Okay. So the way we typically write reactions, okay, that means that we're sitting on the right-hand side of the arrow. And, that should be a double arrow. This is an equilibrium we're talking about. Okay, so you're too far to the right. The reaction is going to shift to the left. It's going to shift toward the reactants, is the way we usually put that. Conversely, if Q is less than K, then you have too much reactants, you're too far over to the left. It's going to shift to the right. It's going to shift toward the products. Okay. Now, this is just in the comparison of Q and K. Okay. If Q is a really, really big number, that means that at equilibrium, it's going to rest far to the right. Okay. A really, really big K means it normally has far more products than reactants, and it's going to sit to the right. But even if K is really, really big, if Q is bigger than K, it's going to move to the left. Okay. That means it's too far to the right, even for something that ordinarily wants to be way over to the right. And if K is really, really tiny, then it ordinarily sits far to the left. It ordinarily has a lot more reactants than products. Okay, but if Q is less than even a very tiny K, then it's still sitting too far to the left, and it's going to shift to the right to end up on the left, but not as far left. Okay, so that's the difference between talking about the size of K and comparing Q and K. Okay. You can have something that wants to be on the left-hand side, but it's too far to the left. Okay, it wants to be on the right-hand side, it's too far to the right. Okay, it'll shift. Even then, it'll shift toward the middle. Okay. All right. So now that we've talked a little bit about Q and K, let's move on to. Let's go ahead and call it for today. We're not quite at 15 minutes, but we're going to cut this video off and come back in our next video to talk about Le Chatelier's principle.